So I'm going to talk about problems that actually have applications in online auctions and, for example, the ad auctions that have come up before. But I'm going to do it like with a toy example that we do to help this guy, Simon. And I'm going to start with giving a flavor of the problem and how it generalizes and what you can do in this area. So I'm going to spend some time on that and then also get to my result there. And let's say this is Simon, and Simon, well, he is not a people person, but he loves cats, and we will help him some issues that he has to actually get a cat at first. So let's say Simon wants a cat, and this is an example I'm going to use to introduce the secretary problem in a way that will be useful later. So even those of you who already know it might at least get a little out of it. So let's start and say Simon wants a cat, and there are people who are currently giving away theirs. Maybe he has found an advertisement for people that want to give away their cat. And he plans to visit these people, and he's making appointments with them in some random order, whatever is convenient. So he visits them, and whenever he goes to see one of them, say Anna, he will see the cat that they offer, and he will know, okay, how much he likes the cat. So there's probably ones that have the wrong character, or he likes the color more or less, and he will know about it once he sees it. And the objective for him, of course, is to get the best one. So he wants to maximize the value of the one he takes. Now also he's gonna be deciding whether or not to take the cat with him, of course, and he cannot expect people to just keep the cat and wait for him and maybe he will come back in 3 months. That is not going to work. They're going to give it away. So he has to decide on the spot, which makes this an online problem. And, well, let's look at it a little bit more theoretically. It's a very famous problem, and it has a very unclear origin. There's papers about just the origin of it. We know the length of a sequence of numbers, and these values just arrive one after another. And, well, there is no assumptions of distribution or anything that they're based on. They can be totally adversarial. Now, we have to decide, once we see a number, whether or not to take it. And we assume that the order of arrival is uniformly at random, because in this area we have to assume something. If we don't, there is nothing known on the values and nothing on the arrival order. This will be unboundedly bad. So this is our assumption. And of course, we're still trying to get the best cat, so to speak. Let's see what Simon does. And this is probably an intuitive way to go at it. At first, I mean, what does he know? He doesn't know anything. But once he goes and sees some cats, he will observe their values. And that is maybe a good way to start. You just go to a few appointments and you wait and see what's there. So let's say he does that. And then he has some feeling for what is good. The 20 there, it looks pretty decent, for example. Now at some point, let's say after seeing half of them, he decides, okay, I'm ready, I know what's good. So after this point, he's actually ready to take action, to decide something. And we put a break there and say, okay, this phase, my information gathering is done. Now, let's say this cat is next. It has a value of 18. Now our actual goal is to pick the best value, and 18 is decent, yes, but it's certainly not the best in the sequence. Why do we know this? Because there has been a 20. So a reasonable way to pick is to say, well, we will only take it if it's the best we've seen so far, right? So let's go on in the sequence. We have this threshold now of 20, and when there's a 6, we certainly say no. However, this 35, he will take home. So this is an algorithm to deal with this problem that is probably very intuitive. And, well, let's do a very simple analysis of what is the magic of this model. So let's say we have looked at half the values. So we know that the probability that the second best one, which is our 20, is actually in the half that we have looked at the beginning, is 1/2. The same holds for the probability that the actual best value that we want is in the part where we do make decisions. And now what happens if both holds? If both holds, so the second best is observed in the beginning, and the best one comes later, we cannot pick anything worse than the second best one. We have to pick any better one, and the only better one here is the 35, so if both holds, we will be optimal. So this happens, of course, with a probability of 1/4, and that means we get a 4 approximation just by the arrival order being random. So this is the principle here, and actually, well, you can improve on this by just moving the point in time where you say, I'm going to start making decisions. And the best way to solve it then gives you E instead of 4. But it's not a different algorithm, it's just a different stopping time for this sample phase. Okay. Now, this problem is very famous, and it has been generalized, and it has been used for a number of things. And what I'm going to talk about is more general settings of this assignment problem that we had here. Let's first start with introducing the bit more complicated problem of online weighted bipartite matching. And let's say Simon has been lucky. He found a whole litter of kittens, right? He took those home, and he cannot keep them because, well, I mean, someone's angry, so he has to give them away. And let's say there's a number of people that are interested, and they will come by his house, and they have valuations for each of the cats that Simon offers. So what we want is to give each of them a good cat, and let's say Simon is interested in the cat's well-being, so he wants to, as an objective, give them away in a manner that will maximize the sum of the values of the chosen assignment, so the social welfare. And of course, it's a matching. For those who don't know, matching, it just means every cat can only go to one bidder, and every bidder only gets one cat. So one-on-one assignment, that is what we want. And again, we will have that the appointments are made in random order, and we have an online problem in the same model as before.
So all the valuation is revealed when the bidder comes?
Exactly. So that means you know about everything that's happened before this point, so about these guys that have already been there, and once the next guy is in your door, he will tell you what are his valuations for all the things that you have. So decide on the spot again, the same thing. Now, of course, this is way more complicated looking, and it's a richer problem than the original one where we had one item. Okay. Actually, quite amazingly, there has been a result that gives the same approximation. It still keeps the ratio of E, just as for the simple problem, and it goes as follows. It's a very simple algorithm. If you remember what we did for the original problem, we just said, okay, we pick something if it is currently looking like the best. Now this algorithm says, well, the best is a little bit more complicated here, but we do the same. So we give the current bidder what he would get in a current best matching over everything we've seen. This is all they do. And this algorithm actually has the same ratio, which I personally find absolutely great. So we have this. The objective is still
probability of getting the absolute best.
As I said before, it's the maximization of social welfare. Let me just, oh no, this is forward, this is back. Where are we? Here. So we maximize the sum of the values that we have assigned, and that is just the same as social welfare.
How are you taking into account what you already allocated?
In this case, I'm going to explain very soon. So there is an issue here, of course, the one you observed, because if I try to give someone a certain cat, it might be that I've already sold it. So let's look at this schematic overview of what happens here. So let's say IT is the set of bidders that I've seen up to time t. So I'm now in time step t, and, well, there's a number of situations that can be the case when IT have arrived, because they have arrived in different orders. I don't know. There's the same probability for every order. But in any case, what the algorithm does, it computes an optimal matching over the graph of every bidder it has seen and all the items. And then it gives the current bidder, may it be this one or that one or that one, just the same thing that he gets in this matching. However, we don't really know about the approximation this will give us because, well, these are order oblivious. So whatever the order is, I will have the same matching that I compute, and every edge that is in this matching has a certain probability that I will try to assign it because this guy might actually be there, this guy might actually be there. They all have the same probability, which means that yes, I have a random subgraph which should hold a reasonable amount of value compared to the overall optimum. And I will also assign every bit of that matching with a certain probability. However, the not so good part here is actually this. Well, it might not be possible because maybe I have done this before in step t-2 or something, and I've given the item away, and now I can't give it away another time. So we might have to account for that. But let's just note as a beginning that what happens here is reasonable in the sense that for every order, as long as IT is the same, so the set of arrived bidders, well, for every order we compute the same matching, but we will assign a different edge from it, right? So this is very reasonable. However, we have to bound the probability that we actually can. Let's look into that shortly. I just want to give a flavor of how the proof goes. So we want to find the probability that when we are in this situation and we want to assign an item j, that it's actually still there, and we can. So let's say, let's look at these circles down there. We are in step t. And let's go backwards through time and see what has happened. Now, what is the probability that we have given the item away just a step before, in t-1? Well, what have we done? We have computed an optimum matching over all of these guys without the t. And one of them, let's say the red one, has clearly been assigned the item. But due to the random arrival order, he might have been anywhere in this sequence. And the probability that this red guy that we gave it to was in exactly this space. This is our probability that we gave the item away in this step. So this probability comes down to exactly 1 over t-1. And we can do the same thing if we just look at the steps up to t-2. So again, we have this somewhat smaller set of guys that have already been there. One of them gets j, but due to the random arrival order, he might be anywhere, and he's in this spot with a probability of 1 over t-2. And if you just do this inductively, you get that for every step you have a constant probability for every item to still be available, which makes our picture like this. So we had this problem here, and this is the way it's fixed in the proof. We have not only that we do the assignment according to a reasonably large matching, and every edge in that matching is considered with a certain probability, but also actually there's a constant probability that this works every time, which in turn just gives the E-competitive ratio. Okay.
So does that mean that you still only give, so you give the item if you can?
Yes.
But still according to when you actually decide what to give, you don't take into account what you already gave. You just don't give it if it's already there.
You try to assign according to this optimal matching. And if you can't, yeah. So bad luck for you if you want the wrong things. Yeah. So this result, if we put it into perspective, is as follows. Vanilla Secretary had the algorithm, well, we sample and we pick the value if it's the so far best. Now for weighted bipartite matching, we sample and we assign a bidder an item if the so far best matching does it. And the paper by Kessler, Radke, Tönnes, and Föcking, they actually do it also for the case that people might want more than one cat, under the assumption that their valuations are submodular. And there it's the same algorithm. They say, okay, I assign this bundle if the so far optimum does so. And it still works the same way. The proof also works the same way. It is completely the same flavor of argument. And in fact, you can generalize this even a little bit more. You can say, okay, if you have bid evaluations that satisfy that every item from a bundle is there with a constant probability, well then, if you also have an offline assignment algorithm that is somehow approximative to the optimum, you can do a secretary algorithm that works just this way, and that will give you a guarantee that is E, and then taking into account the guarantee that A gives you. So this is very nice, but Simon will not completely be happy with it, because in this algorithm, he has no way of knowing if someone that he gives a cat to is gaining a beloved family member or just cheap dinner, right? So he liked to be truthful, and he liked to have a mechanism that incentivizes people to actually tell their true valuations. Now, what does this mean in this surrounding? It's actually easy to make a truthful mechanism in the sense that, well, as long as we just put price tags on everything and say this cat is $10 before someone comes, and then we ask him what he bids and give him the exact thing he wants under these prices, he has no incentive to lie. So it will be like this situation, and this is what Simon says. So this is not too hard. However, it is not really easy to turn these algorithms that I mentioned into a truthful version. And let's just try to think about why. On the one hand, for the original problem, truthfulness is easy because you can go and take your threshold value, the best you've seen, charge that as a price, and it will do the trick. So what's the problem here? And the problem here lies in the way these results were obtained that were previously known about the problem. So there were 8 competitive and e-competitive algorithms by these papers. And the way they are doing their analysis is kind of hard to combine with truthfulness. Let me get a little bit more into this. So the best truthful thing known was actually a logarithmic in the number of bidders, so not that great. And also a weaker notion of truthfulness. There seems to be a problem here. We all thought it might be an actual gap. So this is why. We don't have a single threshold anymore because this is kind of a multi-parameter problem. And then existing algorithms, well, their analysis, as I said, depends on things that make truthfulness hard to achieve. On the one hand, the 8 approximative algorithm does it by choosing always an assignment that has the highest valuation, but without regarding the price. So it does not depend on utility, and it cannot depend on utility. There is no apparent way to do this analysis if you go for utility instead of valuation. And then the second one, the one we talked about earlier, well, they have the issue that Noam just mentioned. If you want something that's gone, and you say so, it will give you nothing. If you want something that's gone, but you still have a small valuation for something that's still there, you're just going to say, okay, I don't want that. That's gone anyway. I'm just going to say, okay, I bid 1 on this other cat. And then I'm going to get that, right? So this incentivizes people to lie. And what we need to do is, of course, we give them what they want in the sense that if I say the truth, the algorithm does what I want it to, so I don't have to deviate. The simple fix is to actually don't offer people things that are not there. And we're going to do just that. Let's do a different version of the algorithm from before that does that. So we have, again, a sampling phase where Simon says, okay, you just come, you just tell me what you bid. I don't tell you any prices, I just observe. So this is what happens. And again, the random order should make this a reasonably good estimate. Now after that, we will have to determine prices. And it would be nice if we still do it like with the best matching. And we are going to use VCG prices. VCG prices are very nice in this regard because they just incentivize people to actually purchase what I want them to purchase to maximize social welfare. We just use that. And we put VCG prices on the cats according to the bidders that have arrived, and of course the set of cats we still have. Now the bidder will pick a utility maximizing item. So let's look at one step. This girl comes, these are my prices, and she says, okay, these are my valuation. Where's the highest utility? Well, she bids 5 on this one and it costs only 1, so utility 4, and we're gonna assign that. Now we have 1 node less on the right side and 1 node more on the left side. So this is everything that happens. And the algorithm, if you just look at the bold parts, it samples, it computes VCG prices, it assigns a utility maximizing item, and then it updates the prices, of course. Okay. Now what we had before looked like this in the schematic overview. What we have now is like this. So there's no need anymore for a constant probability for availability, because everything we offer is available per se. However, we don't really know what happens here. And one observation is that actually these are not the same matchings anymore. So what I compute for any order might differ from the matching I do for a different order. And that means, well, if we are unlucky, we're always going to look at the same bad edges for every subgraph that we look at. So it might be a problem here, which is something we are going to fix by essentially saying, okay, they're not the same, but they are drawn from the same distribution, and then we get the same guarantee. So this is the idea. And as we mentioned earlier, it is nice to have a random subgraph, because that will hold a reasonable portion of the optimal value. But here we have something else. So we have the left side, the arrived bidders, clearly randomly chosen by the arrival order. However, the right side, what is still available, looks like it might depend on the set of the bidders that we have, right? And the only key observation is really it doesn't. And we capture this in something called the Independency lemma, which in a sense, you can think of it replacing this order obliviousness by bidder obliviousness. And implicitly, it will have the same availability probabilities as the original algorithm. So this lemma, it says that whenever I have a fixed time step t and I have that S items are available, the combinations of left side of the graph and right side of the graph that I can have all appear with the exact same probability. So it looks like this. We have our subgraph that we compute composed of left side and right side, and it will be just completely independent. These are 2 independent random variables doing the mechanism. And of course, it's kind of surprising at first that this should hold, but I'm trying to give at least some insight why it makes sense. So as a first intuition, let's look at this situation. So we have this guy, Thai guy, he loves this cat. But of course, when he comes, this cat might be gone. So he might just, you know, have this unlucky situation all the time. But the lemma kind of forbids it. It says that correlations of this form, where this item is almost always sold before he arrives, they cannot exist because it's independent, which means, in turn, there will be a good probability that when he comes, this item will still be there and we can assign it. Okay. So in the competitive ratio, this comes in just 2 places. First, it makes the subgraph that we look at random again, which means it holds a reasonable value. Second, it is that it makes the edges we choose from the subgraphs random again. And then the whole thing comes together very similarly as before. So it will get this picture that we wanted. Okay, so one word about the proof of this. It is kind of hard to think about, so there's a lot of things to handle. What we did in the end is just write it all up in a big, big table. And this is a table of just all the states which depict the subgraphs that we compute on, that the mechanism might ever be in. And if you look at this and you analyze how you can get into any of these states, then you realize, okay, the ways to get there, they depend on the size of the left side and the right side of the graph, but never on the actual valuations in there. And this is just a short example on how to do it. I'll skip it. And in the end, with this observation that you depend on the sizes of it, but never the actual valuations, you get that all the states of the same size, so to speak, appear equally often, and that proves the lemma. So what I want to have as a takeaway pretty much is that the secretary problem, as simple as it is in the beginning, has this kind of magic going on that you can use to, well, to extend it in several directions. There is a lot more than what I showed here. This is even like a small branch. And it's kind of exciting because even if you go towards very complicated stuff, it seems to work just the same. So here we even did combinatorial, taken from the Kesselheim paper, and now truthful works for matching. This is all kind of good, and I'm hoping, of course, that there might be more. But we tried and go towards combinatorial stuff or imposing actual extra constraints on the items you pick. And it seems that this thing where we have replaced the same matching by the same distribution, so to speak, is kind of sensitive. So, for example, Alan and I put in a lot of work to do it for just a restriction to have at most k items, and we got nowhere. So this is sensitive, but still I think the whole principle and how it generalizes is very interesting and very, very useful. So thank you very much for listening. And I'm not going to stand in the way of lunch anymore.
But there is something.
Yes, there is something. Thank you.